Tonight, drift back further than the dinosaurs to the world that made them possible. For 287 million years before the first dinosaur left a footprint, life built itself from nothing. The first eyes, the first bones, the first forests, the first creatures to crawl from water onto land. It nearly destroyed everything it built, twice. This is the Paleozoic era, 4.5 billion years. That is how long Earth existed before anything we would recognize as an animal appeared. The planet formed, cooled, developed oceans, and then spent the overwhelming majority of its existence hosting nothing more complex than single-celled organisms floating in shallow water or clinging to the seafloor in thin bacterial mats. If the entire history of Earth were compressed into a single calendar year, animals with hard bodies and visible anatomy would not appear until the last week of December. Everything before that, the volcanoes, the ancient oceans, the slow chemical transformations of an infant planet, was prologue to a prologue. The Paleozoic era began at the edge of that long silence, approximately 539 million years ago, and it lasted for 287 million years. That number deserves a moment. The entire age of dinosaurs, the Mesozoic, the era that dominates every natural history museum, every documentary, every childhood imagination, lasted roughly 186 million years. The Paleozoic outlasted it by more than 100 million years and built the biological foundation that made the dinosaurs possible. It produced the first eyes, the first bones, the first forests, the first creatures that crawled from water onto land, and it nearly erased everything it built twice before the dinosaurs ever had the chance to exist. The story begins not with a spectacular event, but with a question about absence. Before the Cambrian period opened the Paleozoic, the ocean floor looked almost nothing like what we know today. No fish, no coral, no creature with a recognizable face or a body built for pursuit. The Ediacaran fauna, the organisms that preceded the Cambrian, were soft, frond-like, largely stationary things that fed on organic matter in the sediment. Some resembled quilted mats pressed flat against the rock. Some looked like ferns or discs. For roughly 3 billion years, those were the most complex organisms Earth produced. But here is the problem with that quiet world. It was not simply waiting. It was actively resistant to change, not through any mechanism of defense, but through the basic logic of chemistry. Oxygen in the atmosphere hovered below levels that could sustain anything with a demanding metabolism. The deep ocean held almost none. Any organism that evolved a body requiring more energy than simple diffusion could supply would exhaust itself before it could reproduce. The ceiling on biological complexity was not set by evolution. It was set by the atmosphere, and the atmosphere was not changing quickly. But the Ediacaran fauna, the organisms that appeared in the last fraction of that 3 billion year silence, seemed for a moment to suggest that something new was possible. They were multicellular. Some reached sizes of over a meter. For hundreds of millions of years of microbial monotony, that was extraordinary. But the fossil record does not show them evolving into anything more. It shows them existing for roughly 40 million years and then disappearing, replaced not by their descendants, but by something categorically different. Organisms with shells, with mouths, with the capacity to pursue and to flee. But the question the Ediacaran fauna raises is one the fossil record struggles to answer cleanly. If multicellular life appeared during the Ediacaran, why did complexity stall there for tens of millions of years before the Cambrian? Why did the ocean floor spend so long populated by soft, sessile organisms with no predators and no apparent pressure to become anything other than what they were. Something was holding the door shut, and whatever it was not biological. It would not move until a set of conditions no single organism could influence had finally, slowly converged. The world before the Cambrian was not underdeveloped. It was sufficient on its own terms, sufficient in a way that had no use for complexity, because complexity had no advantage yet. Bacteria dominated the oceans for 3 billion years, not because evolution was slow, but because the conditions that reward complexity, sufficient oxygen, active predation, genuine competition, simply did not exist. The Ediacaran organisms that appeared after the snowball Earth events were soft, largely immobile, and filtered nutrients from sediment. They left almost no descendants. They were not a stepping stone towards something better. They were an experiment the planet tried and then quietly abandoned. What the world before the Cambrian shows is that life does not build toward anything on its own. It fills whatever space chemistry and physics allow, and for 3 billion years, that space was narrow. Oxygen was too scarce for large, energy-hungry bodies. No predators existed to drive the evolution of defense, and without the need to defend, there was no pressure to develop speed, armor, or the senses needed to detect a threat moving toward you across open water. The ocean floor was a quiet mat of microbial life, and that quiet meant stable, and stable meant unchanged for longer than the human mind can meaningfully picture. What ended that silence was not a single mutation or a fortunate accident. It was a planetary chemistry shift. Accumulated oxygen in the deep ocean, finally crossing a threshold, combined with the mineral richness left behind by the melting of snowball Earth glaciers, that made it physically possible for larger, more energetic, more complex bodies to exist. The stage did not fill because life decided to fill it. The stage filled because the rules of the stage changed. And once they changed, 3 billion years of biological patience collapsed into roughly 20 million years of transformation so rapid that scientists still argue about what exactly lit the fuse. If this kind of slow, deep history is what you come here for, a like on this video helps more people find it. That's all. No interruption. The story continues. But the silence that preceded the Cambrian is only half the story. What broke it was not a gradual awakening. It was a transformation so sudden and so total that it produced, within a single compressed window of geological time, the body plans of nearly every animal group alive today, and several that exist nowhere on Earth anymore. And at the center of all of it was something whose appearance changed the logic of survival for every organism in that ocean, permanently. The ocean learned to see. What happened next was not progress, it was war. The Cambrian period opened approximately 539 million years ago, and within roughly 20 million years ago, a blink by geological standards, the ocean transformed from a place of near total biological simplicity into something that would be recognizable to a modern marine biologist in its fundamental architecture. Predators, prey, shells, pursuit and escape, all of it appeared in what is, on the scale of Earth's history, essentially a single moment. Geologists and paleontologists have a name for this, the Cambrian explosion. The name is accurate in the sense that the diversity of animal body plans that emerged during this interval has never been matched before or since. More than 80% of the major animal groups recognizable today, the phyla, the broad categories of body plan trace their origins to this period. Arthropods, mollusks, echinoderms, chordates, all of them appeared within the same narrow window of geological time. The ocean went from hosting a handful of soft-bodied organisms to hosting a full cast of complex, interacting, competing life forms in an interval that represents less than 0.5% of Earth's total age. The fossil record of the Cambrian is preserved in extraordinary detail in 2 places. The Burgess Shale in British Columbia, discovered in 1909 and dated to approximately 508 million years ago, preserves soft tissues, guts, muscles, in fine-grained black shale in a way that should not be possible and yet is. The Xinjiang biota in Yunnan province, China, dated to approximately 518 million years ago and discovered in 1984, is older than the Burgess Shale and preserves Cambrian animals in 3-dimensional detail that allows researchers to reconstruct their internal organs and nervous systems. These 2 sites are windows into a world that was, by any measure, alien, populated by creatures that fit no modern category, and that scientists spent decades simply trying to place right side up. But the Cambrian explosion creates a problem that has unsettled paleontologists for over a century. If the trigger was oxygen, oxygen had been accumulating for hundreds of millions of years before the Cambrian. If the trigger was the chemical richness left by melting snowball Earth glaciers, those glaciers had been melting for tens of millions of years before the explosion began. Neither condition appeared suddenly. Both had been building gradually. But the explosion itself was not gradual. The body plans appeared within a window of geological time so narrow that it barely registers on the scale of Earth's history. And scientists have never reached consensus on why that window opened when it did, and not earlier. But the predation hypothesis introduces its own complications. If predation drove the arms race, something had to be the first predator, and the first predator appeared in an ocean where nothing had yet evolved the defenses that predation would eventually produce. The shells, the spines, the armor of the Cambrian came after predation began, not before, which means the first predator hunted in an ocean full of soft, undefended prey. And it means the arms race had a starting point, a moment when the ocean went from having no hunters to having one, and everything that followed was a consequence of that single transition. But Anomalocaris itself resists easy categorization. Its fossils were found in pieces across multiple sites over several decades, and each piece was so unlike any known animal that scientists classified them as entirely separate organisms. Only when a complete specimen was recovered did the full predator become visible, and even then, Anomalocaris belonged to no modern group. It was a member of the Radiodont lineage, a group with no living representatives, a body plan that succeeded for millions of years and then ended. Most of what the Cambrian produced was not ancestry. It was an experiment without continuation. Every animal in that ocean faced a pressure that had never existed before. Once Anomalocaris could genuinely see, not detect light, but track movement across open water with compound eyes on stalks. Hiding became valuable, armor became valuable, and the ability to move quickly in the right direction became the difference between surviving long enough to reproduce and not. The trilobite that could roll into a defensive ball lived longer than the one that could not, and Waiwaxia covered its soft body in scales and spines, not as decoration, but because being difficult to swallow bought time, and time meant offspring. Hallucigenia was so strange that the first scientific reconstruction placed it upside down. What paleontologists initially believed were its legs were in fact defensive spines on its back, and what they thought were dorsal appendages were its actual walking legs. Even corrected, the animal remains one of the most disorienting creatures in the fossil record. Anomalocaris itself was initially described as 3 separate animals, its circular mouth catalogued as a jellyfish, its grasping appendages as shrimp tails, its body as a sponge. Only when complete specimens were recovered did the full predator become clear. 1 meter long, compound eyes, segmented grasping arms, a ring of crushing plates for a mouth capable of breaking trilobite shells. The Cambrian creature that answers the deepest question is the least impressive one. Picaia, a blade-like swimmer roughly 5 centimeters long, carried a notochord, a stiffening rod running the length of its body that is the structural precursor to the vertebral column. It was not armored and had no obvious weapon, surviving in a sea full of grasping appendages and crushing mouths by being small, flexible, and capable of coordinated movement. That notochord was the architectural prerequisite for every vertebrate that ever lived. Every fish, every amphibian, every reptile, every mammal. The Cambrian did not just produce strange creatures, it produced the blueprint that everything with a backbone would eventually build on. But the arms race that the Cambrian ignited did not burn itself out, it expanded. The ocean that emerged from the Cambrian was already complex by any previous standard. But what the next 40 million years produced made the Cambrian look like a rehearsal. Sea levels rose, shallow water spread across continents, and in that warm, sunlit expanse, life built something that had never existed before. An ocean organized into layers, with specialists at every depth and a predator large enough to hunt from above. The most productive marine ecosystem in Earth's history was assembling itself, and it would take only a shift in the planet's temperature to erase it. After the Cambrian, the ocean did not pause. The burst of biological innovation that had produced the first shells and the first true predators continued into the Ordovician period, which ran from approximately 485 to 444 million years ago. Sea levels during the Ordovician were among the highest in Earth's history. Vast, shallow inland seas spread across the continents, warm and sunlit, offering the kind of stable, nutrient-rich conditions that allow ecosystems to grow not just in size, but in structural complexity. For roughly 40 million years, marine life expanded into every available layer of the water column and every corner of the sea floor. The Great Ordovician Biodiversification Event is the formal name for what happened during this period, and the word diversification understates it. The number of marine animal genera roughly tripled. Reef-building corals appeared for the first time. Tabulate and rugose corals that constructed the first biological reef frameworks in Earth's history, providing shelter, concentrated food sources, and physical structure that turned flat sea floor into layered habitat. Trilobites, which had already been present since the early Cambrian, spread into hundreds of new species occupying every conceivable ecological role, from burrowing deposit feeders to active midwater predators. What the Ordovician produced was not just more life, it produced an ocean organized into something resembling a modern ecosystem, with distinct layers, specialized occupants at each layer, and the kind of intricate feeding relationships that make a biological community stable enough to persist for tens of millions of years. The ocean had become a place where a creature's position in the water column, how deep it lived, how it fed, how it moved, determined everything about its anatomy and its survival. That degree of organization was new to the ocean. The Cambrian had written the first draft. The Ordovician was the revision that made it legible. But the Ordovician prosperity carried a structural vulnerability that the organisms living inside it had no way to perceive. The entire biological architecture of the Ordovician Ocean depended on stable sea levels, stable temperatures, and the continued availability of warm, sunlit, shallow water. The crinoid meadows could not survive without the seafloor conditions that the high sea levels maintained. The reef communities required specific water chemistry and temperature ranges to build and sustain their calcium carbonate frameworks. Camarasaurus needed a food web dense enough to support a 9-meter predator at its apex. Every layer of the Ordovician ecosystem was calibrated to conditions that had been consistent for tens of millions of years, and that calibration was its weakness. But the continents were moving. The landmass that would eventually become Africa was drifting southward across the pole, and as it did, it began accumulating ice. Glaciation on a continental scale locked seawater into ice sheets. Sea levels dropped. The shallow marine habitats that had hosted the crinoid meadows and the reef communities were drained as the water retreated. The warm, sunlit seafloor that the Ordovician ecosystem had been built on became cold, exposed rock. The organisms that depended on those conditions had nowhere to go, because the conditions themselves had ceased to exist. But the glaciation did not arrive as a sudden event. It built gradually, which meant the ecosystem experienced not a single lethal blow, but a prolonged deterioration. Habitats shrinking, food webs thinning, species ranges contracting toward whatever pockets of survivable conditions remained. Each organism was responding to local conditions, and local conditions were worsening in ways that no local adaptation could address. The Ordovician extinction killed not because it was fast, but because the changes that drove it operated at a scale that made biological response impossible. Crinoid meadows covered Ordovician seafloor so densely that when the animals died over millions of years, their accumulated calcium skeletons compressed into thick limestone beds, the same limestone that forms the building stone of historic structures across the American Midwest and the British Isles today. Those limestone layers are a record of biological abundance, the physical remains of ecosystems so productive they left their architecture in the rock. At the top of that ocean swam Camarasaurus, an orthoconic nautiloid with a straight conical shell reaching up to 9 meters in length, the largest known animal of the period. It regulated its position in the water column by filling internal shell chambers with gas, hovering at whatever depth offered the best angle of approach, then descending to seize the trilobites and brachiopods below. The eurypterids, the sea scorpions, were already diversifying beneath it, with Megalograptus ohioensis reaching 80 centimeters and scouring the ancient shorelines of what would one day become the eastern United States, using long spiny arms to seize prey from both the sediment and the water column above. The pattern the Ordovician demonstrates is one the fossil record repeats without exception. As ecosystems grow more complex and food becomes more available, size and specialization become the dominant strategies. Around 445 million years ago, glaciation locked vast quantities of seawater into ice. Sea levels dropped. The shallow marine environments that had supported the most biologically productive oceans in Earth's history to that point were drained. Ocean temperatures plummeted. The chemical stability that Ordovician life had been built around shifted too rapidly for ecosystems to adjust, and approximately 85% of marine species went extinct. The first major mass extinction in animal history did not arrive as a sudden impact. It arrived as ice, a falling sea level, and the quiet disappearance of the warm, shallow water where almost everything alive had learned to live. But the ocean that survived the Ordovician extinction was not the ocean that had existed before it. 85% of marine species were gone. What rebuilt itself did so from whatever fragments remained, and, in the process, the world that assembled in the aftermath of that first great dying began pushing life toward a boundary it had never crossed before. Not deeper into the ocean, not into colder water or darker seafloor, outward, onto the bare, hostile, UV-blasted surface of land. Something was beginning at the water's edge, and it had no precedent in the history of the planet. The Ordovician extinction left the ocean diminished. Around 85% of marine species were gone. The crinoid meadows thinned. The reef communities collapsed. The trilobite diversity that had accumulated across 40 million years of the Ordovician was drastically reduced. The Silurian period, which ran from approximately 444 to 419 million years ago, was the recovery. But recovery in Earth's history rarely means returning to what existed before. It means rebuilding with what survived in a world whose conditions have shifted. The ocean did recover. Sea levels rose again as the glaciers that had triggered the extinction melted. Oxygen levels in the water stabilized. Reef-building organisms returned, though the reef communities of the Silurian looked different from those of the Ordovician, built by different organisms filling similar roles. Cephalopods continued to dominate as apex predators. Trilobites persisted, though in reduced numbers and diversity. Eurypterids, the sea scorpions, grew larger and more varied, with some species reaching nearly 2 meters and becoming among the most formidable hunters in the Silurian Ocean. But the defining story of the Silurian was not happening in the water. It was happening at the water's edge, and then just beyond it, in places where no complex life had ever existed before. The continents of the Silurian were not the continents we know. They were arranged differently, clustered in ways that created large stretches of tropical and subtropical coastline, warm and wet and periodically flooded. On the exposed surfaces of those coastlines, something was beginning. Not an animal, not a creature capable of moving or hunting or fleeing. Something far smaller and far slower, rooted in place, drawing sustenance from dry ground in a way nothing had managed before. But the land that organisms were beginning to colonize in the Silurian was not hospitable in any meaningful sense. The atmosphere, though improving, still lacked the ozone layer density that modern land organisms depend on to filter ultraviolet radiation. The surface temperature of exposed rock under direct Silurian sunlight was lethal to most tissues. Water evaporated from any exposed surface with a speed that the physiology of marine organisms, shaped entirely by immersion in seawater, had no answer for. Cooksonia survived on land, not because the land was suitable for it, but because its vascular tissue gave it just enough control over its internal water supply to persist in conditions that would have killed its ancestors. But the arthropods that followed Cooksonia onto land faced a different and more immediate problem. Their exoskeletons, evolved for the buoyancy of water, bore their body weight poorly on dry ground. Respiration through gills ceased to function in air. The reproductive strategies that worked in the ocean, releasing eggs into the water column, relying on aquatic larvae as an intermediate stage, had no equivalent on a dry surface where eggs desiccated within hours of exposure. Every organ system these animals possessed had been shaped by millions of years of aquatic life, and none of those systems worked the same way on land. But the ocean itself was becoming a reason to leave. The Silurian was the period in which the ocean first developed a genuine apex predator tier, large, fast, and capable of processing hard-shelled prey in ways the Ordovician Ocean had never seen. For organisms small enough to be prey, the land, despite its physiological demands, represented something the ocean no longer offered. The Silurian coastline was a brutal frontier, but the ocean behind it was becoming something worse. Life crossed from the ocean to land reluctantly in pieces, for reasons that had nothing to do with any kind of forward plan. Cooksonia, the earliest known vascular plant, stood only a few centimeters tall and had no leaves, no true roots, and no seeds. But it carried vascular tissue, an internal system of tubes capable of transporting water upward against gravity. And that single innovation was the structural prerequisite for every plant that would follow it. Without vascular tissue, photosynthetic life on land was limited to thin microbial crusts that could not grow tall and could not survive far from standing water. With it, the continents became something plants could genuinely colonize, and colonized land began chemically transforming the surface, roots fracturing rock, fungi releasing bound minerals, nutrients washing into rivers and eventually reaching the sea. The arthropods followed, not as a planned migration, but as opportunistic incursions, creatures moving briefly onto land to escape the increasingly dangerous ocean, or to find food, or to lay eggs away from predators in damp soil near the water's edge. Megamastax, appearing around 423 million years ago in what would one day become China, was among the first jawed predators in vertebrate history, its teeth capable of crushing the armor of other fish in ways that no jawless filter feeder had ever managed. Pterygotus, a eurypterid approaching 2 meters, is believed to have burrowed into soft substrate and burst upward to seize whatever passed overhead. 2 worlds were developing in parallel without awareness of each other, an ocean becoming more competitive and more lethal, and a land slowly opening as a frontier with fewer predators and untapped resources, but with physiological demands that life had barely begun to meet. Neither world knew what the other would eventually become. The organisms moving between them were making local survival decisions, and those decisions, accumulated across millions of years and countless generations, would eventually close the distance between the sea and the shore for good. But the land that life was beginning to colonize in the Silurian was still, in every practical sense, a frontier with no rules. The ocean, meanwhile, was about to produce the most powerful vertebrated predators the world had yet seen. Animals 8 to 9 meters long, with shearing blades instead of teeth and a bite force comparable to a large crocodile, capable of cutting through the armored bodies of other fish as though the armor were not there. That predator was the apex of an arms race that had been escalating for tens of millions of years. And somewhere in the shallow rivers of what would one day become the Canadian Arctic, a creature was taking shape that carried something in its fins that neither it nor anything around it had any use for yet. The limbs that would eventually walk the earth were still underwater, but not for much longer. The Devonian period ran from approximately 419 to 359 million years ago, and it is often called the Age of Fishes, a label that is accurate but incomplete. The oceans of the Devonian were dominated by fish in a diversity that has never been equaled in the subsequent history of vertebrate aquatic life. Jawed fish, which had first appeared in the Silurian, radiated explosively through the Devonian into every ecological role available in both marine and freshwater environments. The placoderms, armored fish encased in interlocking bony plates, occupied niches from small bottom-dwelling scavengers to the apex predators of the open ocean. Sharks appeared in the Devonian fossil record for the first time, initially as minor components of communities dominated by the more spectacular armored groups. The fish of the Devonian were not the fish we recognize today. The dominant groups, the placoderms and the acanthodians, have no living descendants. They were evolutionary experiments that succeeded for tens of millions of years and then vanished, leaving the ocean to lineages that would eventually become the fish of the modern world. What the Devonian Ocean preserved in extraordinary detail in deposits like the Cleveland Shale of northeastern Ohio was a snapshot of vertebrate life at a moment when the body plans available to fish were far more varied than anything that exists today. Some had heads fused to their bodies. Some had hinged skulls that opened by tilting the head upward rather than dropping the jaw. Some had armor that covered only the front half of their bodies, leaving the muscular tail exposed for propulsion. On land, the Silurians' tentative first steps had become something larger. Plants had diversified dramatically from the simple leafless stems of Cooksonia into true trees, organisms with woody secondary growth. Genuine root systems that penetrated meters into the soil, and broad leaf canopies that competed for sunlight. Archaeopteris, the first recognizable tree, spread rapidly across the late Devonian land surface, forming the first genuine forests in Earth's history. Those forests were already changing the world in ways that nothing living in them could detect. But the Devonian Ocean was changing in ways that the organisms living inside it could not detect. The forests spreading across the land surface were altering atmospheric chemistry on a scale that affected ocean temperatures, circulation patterns, and the chemistry of the shallow marine environments where most Devonian life was concentrated. The ocean was cooling. The reef communities that had rebuilt since the Ordovician extinction were moving into conditions they had not been shaped for. And the placoderms that dominated the water column were dependent on food webs that the cooling was beginning to disrupt. But Tiktaalik appeared at almost exactly the moment the Devonian Ocean was beginning to fail. The late Devonian extinction, unfolding in pulses between roughly 375 and 360 million years ago, eliminated approximately 70% of species, particularly the reef communities that had recovered from the Ordovician extinction and rebuilt across the Silurian and early Devonian. The placoderms, which had dominated the Devonian Ocean for tens of millions of years, were gone by the end of the period. Dunkleosteus itself went extinct. The ocean that had produced the most spectacular vertebrate predators yet seen simply dismantled itself over a few million years. But the vertebrates, moving onto land in the late Devonian, were not moving toward a clear destination. The terrestrial world they were entering was unstable, shaped by the same planetary forces that were dismantling the ocean behind them. What those animals were moving into, and whether the land would prove any more durable than the ocean they were leaving, was not a question any of them could ask. It would take millions more years to find out whether the transition was an escape or simply a change of venue. Dunkleosteus is what an arms race produces when it runs long enough with no ceiling. 8 to 9 meters long, with no teeth in the conventional sense. Only self-sharpening bony shearing blades, generating an estimated bite force of 5 to 6,000 newtons, concentrated into edges capable of cutting through the plated armor of other fish. It left bite marks on prey. It produced regurgitated pellets of indigestible fish armor, exactly as modern raptors produce pellets of fur and bone. And the ocean it dominated was not a stable ecosystem, but a contest between ever thicker armor and ever more powerful jaws that had been escalating for tens of millions of years before Dunkleosteus arrived at its apex. Around 375 million years ago, Tiktaalik rosier appeared in shallow, warm rivers of what is now Arctic Canada, and its body answered the question of how a vertebrate leaves the water. Its scales, gills, and fins were fish anatomy, but its pectoral fins contained a shoulder, an elbow, and a wrist, the full complement of joints that allows a body to push itself upward from the ground. And its neck could turn independently of its torso, a feature unknown in fish. Neil Shubin, who led the discovery team, described it as a fish that could do push-ups. The limbs came first, and the land followed later, not as a destination, but as an accidental consequence of adaptations that had evolved for pushing through dense aquatic vegetation in shallow water. The vertebrates did not leave the ocean because they intended to. They left because the adaptations they had already developed happened across millions of years and multiple lineages to also work on dry ground. And the forests of Archaeopteryx, which had been drawing down atmospheric CO2 through deep root weathering and cooling global temperatures, had already prepared that ground for them. The same forests that helped trigger the late Devonian extinction, which eliminated approximately 70% of species, were the ones that built the terrestrial world vertebrates eventually inherited. But the land that the first vertebrates crawled onto in the Devonian was not the land they would inhabit for long. A new world was assembling, one with an atmosphere so altered by the forests growing across it that the biological rules governing body size were about to be suspended entirely. The Carboniferous was not a continuation of what had come before. It was a different planet, operating by different chemistry, producing organisms that have no equivalent in any ecosystem alive today. And hidden inside one of the least impressive creatures in that entire alien world was an invention that would eventually free every vertebrate from the last constraint, tying it to the water. The Devonian ended with extinction, approximately 70% of species gone in a series of pulses between roughly 375 and 360 million years ago. And the world that emerged from it was a changed one. The Carboniferous period, running from approximately 359 to 299 million years ago, inherited a planet whose atmospheric chemistry was already shifting. The vast forests of the late Devonian had been drawing carbon dioxide out of the atmosphere through root weathering and organic burial. Oxygen levels, which had been rising since the late Devonian, continued to climb into the Carboniferous, driven by an expansion of plant life across the continents that dwarfed anything that had come before. The continents in the Carboniferous were positioned differently than they are today, clustered near the equator in a configuration that produced a warm, persistently humid global climate, ideal conditions for the growth of the vast lowland forests that would define the period. These were not forests of oak and pine. The dominant trees were lycopsids, club mosses, that had evolved tree-like growth forms with trunks reaching 30 to 50 meters tall and bark covered in distinctive diamond-shaped patterns. Growing alongside them were giant ferns, horsetails reaching 20 meters, and early seed-bearing plants beginning to diversify into the drier ground at the forest margins. The result was a continuous, globe-spanning belt of swamp forest unlike anything before or since. The animals that lived inside those forests were stranger than anything a modern eye would expect. The Carboniferous is the period in which terrestrial life, freed from the water by the amniotic egg and fueled by an atmosphere richer in oxygen than any land animal has breathed since, began exploring the upper limits of what bodies are physically capable of becoming. What those limits turned out to be was, by any modern standard, unsettling. But the same oxygen that produced giants made the Carboniferous world catastrophically fire-prone. Wildfires ignite more easily and burn more intensely as oxygen concentration rises above roughly 25%. At 35%, the threshold for ignition drops to a level where even wet vegetation can combust under the right conditions. The fossil record of the Carboniferous contains abundant evidence of charcoal, fossilized wood burned by ancient fires, scattered through the coal seams that the forests themselves would eventually become. The world that produced the largest insects in Earth's history was also a world that burned repeatedly, and those fires were not anomalies. They were a structural feature of an atmosphere that had been pushed beyond any previous state. But Hylonomus, small and easily overlooked among giants, carried something that none of the organisms around it possessed, a solution to a reproductive problem that the forest itself was quietly making more urgent. The amphibians sharing its habitat were biological successes in every way that the Carboniferous rewarded, but they remained tethered to moisture for one critical stage of their life cycle. What Hylonomus had changed about that dependency was not yet visible in its size or its behavior. It was visible only in what it could do that nothing around it could, and in a forest that was more flammable than any forest before it, that difference was beginning to matter. But the Carboniferous forest felt permanent. It had covered the equatorial continents for tens of millions of years, and the organisms inside it had been shaped entirely by its persistence. The giant lycopods reached 50 meters and spread their spores across a continuous belt of swamp that seemed, from inside it, like the fixed condition of the world. Nothing in the biology of any Carboniferous organism registered what the slow movement of continents was doing to the circulation patterns that kept the forest wet. The forest did not know it was temporary, neither did anything living in it. Atmospheric oxygen reached approximately 35% during the Carboniferous, and the reason it reached 35% is a single molecule, lignin, the structural polymer that gives wood its rigidity. Lignin was new. The plants had evolved the biochemical pathway to produce it, but the fungi capable of breaking lignin down had not yet evolved the specific enzymatic machinery to decompose it efficiently. When Carboniferous trees fell into the oxygen-poor swamps that covered the continents, they did not rot in any meaningful time frame. They accumulated, buried by sediment faster than decay could consume them, locking carbon into the ground and leaving oxygen in the air. The coal seams mined across Pennsylvania, Yorkshire, and the Ruhr Valley are the compressed remains of those trees, and the carbon released when coal combusts is the same carbon those trees pulled from the Carboniferous atmosphere over 300 million years ago. The biological consequences were direct. Meganeura, a dragonfly relative, had a wingspan up to 70 centimeters, the size of a modern crow. Arthropleura, a millipede relative, reached over 2.5 meters in length and 50 centimeters wide, leaving trackways preserved in coal measures across Europe and North America. Insects breathe through tracheal tubes that rely on diffusion, and diffusion becomes more efficient as oxygen concentration rises, relaxing the constraint on how large an insect's body can grow before oxygen delivery fails to reach its center. The decisive innovation of the Carboniferous was not any of those giants. It was a small lizard-like creature 20 centimeters long, living among the hollow trunks of fallen trees in what would become Nova Scotia. Hylonomus carried the amniotic egg, a package of protective membranes and shell that allowed an embryo to develop fully on dry land without access to standing water. For the first time in vertebrate history, reproduction required no return to the ocean or any other body of water. The last biological tie that bound vertebrates to their aquatic origins was cut, and every reptile, bird, and mammal that followed inherited that solution. But the world the Carboniferous built was not permanent. Nothing in the geological record is permanent, and the continuous tropical forest that had covered the equatorial continents for 60 million years was no exception. What ended it was not a catastrophe in the conventional sense. No asteroid, no eruption, no single event with a clear date. What ended it was continental drift, operating at its ordinary geological pace, quietly rerouting the moisture that the forest depended on. The collapse, when it came, did not destroy all life equally. It destroyed the life that needed what the forest provided and handed the world to the life that did not. The Carboniferous swamp forests covered most of the landmass that would eventually become Europe and North America for roughly 60 million years. They were not a marginal habitat. They were the dominant terrestrial ecosystem of the period, the environment in which most of the large land animals of the Carboniferous spent their entire lives. The giant insects, the diverse amphibians, the early reptiles clinging to hollow trunks and hunting through the leaf litter. The forests were not a backdrop to life. They were the structure that made Carboniferous life possible, providing the conditions that amphibians had been shaped for across tens of millions of years, the dense plant matter that sustained the herbivores, and the physical complexity that gave predators places to hunt and prey places to hide. Pangaea was assembling. Throughout the Carboniferous, the continental plates that had been drifting toward each other since the Devonian were continuing their slow convergence, closing the ancient oceans between them and raising mountain ranges where their edges collided. The Appalachian Mountains, whose rounded peaks in the eastern United States today represent the eroded remnants of a once towering range, rose during this period as North America and the landmass that would become Europe ground together. These mountains disrupted atmospheric circulation patterns and began to alter the flow of moisture across the interior of the forming supercontinent. The climate was shifting. The continuous tropical wetland that had sustained the coal forests for tens of millions of years was not as stable as it appeared. The forest did not know this. The amphibians living in it did not know this. The giant millipedes crawling through the leaf litter, the hawk-sized dragonflies hunting above the canopy, none of them had any mechanism for detecting what was coming. Around 307 million years ago, the world they had been built for began to fragment. But the fragmentation did not announce itself. The forest did not thin gradually across the whole landscape simultaneously, giving organisms time to adjust. Instead, the collapse was patchy. Some regions dried faster than others, some forest patches persisted longer, and and dry ground appeared between patches that had previously been continuous. That patchiness was precisely what made the collapse so consequential, because it created a landscape of barriers rather than a landscape of gradients. And barriers do not allow the slow adjustment that gradients permit. But the amniot lineages inheriting the opening landscape were not more sophisticated than the organisms they were replacing. They were not faster or larger or equipped with any obvious advantage that would have predicted their eventual dominance. What separated them from the amphibians was a single biological feature whose importance the Carboniferous had not yet fully revealed. And the only reason that feature was now decisive was that the world had changed in exactly the way that made it matter. The accident was not in the organisms. The accident was in the timing. But the lineages diverging in the aftermath of the collapse had not yet become what they would eventually produce. The world that had opened was vast, largely emptied of competition, and available to whatever could cross the new dry corridors first. What those lineages would eventually make of that opportunity, and how long it would take the planet to present them with the next set of conditions that would force them to change again, remained entirely open. The collapse did not affect all life equally, and that asymmetry is what reorganized the planet. For amphibians, the fragmentation of the continuous tropical forest into isolated patches was a hard boundary. Their eggs had no protective shell and would desiccate on dry ground. Their larvae required standing water to develop. When dry corridors opened between forest patches, as Pangaea's assembly diverted ocean currents and imposed more pronounced dry seasons, amphibians could not cross. Each remaining forest patch became an island, and island populations that cannot exchange individuals with neighboring populations eventually collapse. The organisms that had dominated terrestrial vertebrate life for tens of millions of years were confined to wherever water remained. For amniotes, the lineage carrying the hard-shelled egg, those same dry corridors were habitat. They could cross ground that amphibians could not, and colonize isolated forest patches before amphibians could recolonize them. The collapse handed the continents to two lineages that had diverged from a common ancestor only recently: the reptiles, whose descendants would eventually include dinosaurs, birds, and crocodilians, and the synapsids, whose descendants would eventually include every mammal alive today. The synapsids came to dominate terrestrial life for the first 100 million years of amniote history, not because they outcompeted anyone in a direct contest. Their dominance was the consequence of a climate accident, removing the organisms that had been there first. The world that the synapsids inherited was a world reorganized by a dying forest, and what grew in that forest's place would eventually produce creatures with warm blood, differentiated teeth, and bones that had once been part of a jaw. But the lineages that inherited the post-collapse world had only just begun their transformation. The Carboniferous had produced the first reptiles and the first synapsids. The Permian would take those two groups and run them through 50 million years of the harshest continental conditions the planet had produced: searing interiors, unpredictable rainfall, shrinking coastlines. And what came out the other side was something the Earth had never seen before. One lineage was approaching the biological boundary between reptile and mammal so closely that the fossil record struggles to place the line. The world before the dinosaurs was not waiting for anything. It was almost finished building its replacement. The Permian period ran from approximately 299 to 252 million years ago, and by the time it began, Pangaea was essentially complete. The supercontinent that had been assembling since the Devonian now stretched from pole to pole as a single continuous landmass surrounded by a single global ocean called Panthalassa. This geography had consequences that cascaded through every living system on Earth. Coastlines, which had previously wrapped around numerous separate continents and created vast stretches of shallow marine habitat, were now reduced to the outer margins of a single enormous land body. The interior of that land body, hundreds of millions of square kilometers of it, lay so far from the moderating influence of the ocean that the seasonal temperature swings were more extreme than anything most terrestrial organisms had previously experienced. The giant insects of the Carboniferous were already declining as oxygen levels gradually fell from their Carboniferous peak. The vast swamp forests that had sustained those oxygen levels were now restricted to patches near the coasts, replaced in the drier interior by drought-tolerant seed plants, early conifers, seed ferns, and other gymnosperms, whose needle-like leaves and waxy cuticles were adaptations for conserving water in a landscape where rain was scarce and unpredictable. The world looked different, felt different, and operated by different ecological rules than the one the Carboniferous had produced. Into that harsher world stepped the synapsids, the lineage that had diverged from the reptiles back in the Carboniferous and spent the intervening millions of years diversifying quietly while the amphibians still dominated. The Permian was the era in which the synapsids came fully into their own, spreading across every continent, filling every size class from small insectivores to multi-meter apex predators, and beginning the slow anatomical transformation that would eventually, after another 50 million years of refinement, produce something that the Permian world had never seen before. But the very features that made cynodonts nearly mammalian also made them metabolically expensive. Warm-bloodedness, if they possessed it, required more food than a cold-blooded animal of comparable size. Differentiated teeth capable of processing food efficiently were an advantage in a world with enough food to process, but a liability when food became scarce. The Permian interior was not a landscape of abundance. It was a landscape of extremes, searing summers, cold winters, and unpredictable rainfall that made plant growth seasonal and patchy. The cynodonts were biologically sophisticated, and biological sophistication is expensive to run. But the dicynodonts that grazed the Permian floodplains were filling an ecological role that had never existed at that scale before. Large, abundant herbivores covering vast continental interiors. Large, abundant herbivores change landscapes. They consume vegetation faster than it can regenerate in dry conditions, exposing soil to erosion, altering the local water retention of the ground, and creating feedback loops between animal population size and the carrying capacity of the land they depend on. The Permian was not just a world shaped by climate. It was a world where the animals themselves were beginning to influence the conditions that sustained them, and the margin between a functioning ecosystem and a collapsing one was narrower than the surface suggested. Late Permian cynodonts had differentiated teeth, canines for puncturing, post-canine teeth with complex cusps for processing food, in a configuration essentially identical to early mammal teeth. They had a secondary palate, a shelf of bone separating the nasal passage from the mouth, allowing them to breathe while chewing, a feature absent in reptiles. Several bones that had functioned as jaw elements in earlier synapsids were already migrating toward positions where they would eventually become the hammer and anvil of the mammalian hearing system. They likely had fur and were almost certainly producing more body heat than a cold-blooded animal of comparable size. In every practical biological sense, the line between cynodont and mammal was a matter of a few bones in the skull, and even paleontologists treat that boundary as somewhat arbitrary. Dimetrodon, which appears in countless toys and educational materials alongside dinosaurs, was not a dinosaur and was not a reptile in modern classification. It was a synapsid more closely related to a human than to any dinosaur, reaching 4 to 5 meters and dominating the early Permian food chain before going extinct, well before the period ended, replaced by more advanced therapsids. The gorgonopsids that followed became the first saber-toothed predators in Earth's history, with Inostrancevia reaching over 3.5 meters and hunting the massive dicynodonts that graced the Permian landscape in herds ranging from rat-sized to hippopotamus-grade. The world immediately before the dinosaurs was not a primitive or underpopulated waiting room. It was a complete biosphere built on 290 million years of compounding evolutionary innovation, populated by animals sophisticated enough in physiology, ecology, and behavior that the boundary between them and true mammals was more a definitional line than a biological cliff. What stopped that trajectory was not competition from a better adapted group. It was the planet itself. But the world the Permian built, that layered, sophisticated, nearly mammalian biosphere, was sitting on top of something it could not detect. In what is now Siberia, a process was already underway that would not announce itself until it was far too late for anything alive to respond. The Permian biosphere had survived the end of the Carboniferous forests, the decline of giant insects, the oxygen drop that killed the largest arthropods in Earth's history. It had been tested and held. What was coming was not a test. It was a cascade, and the very sophistication that made the Permian world so biologically impressive was the same quality that made it so catastrophically vulnerable to what was about to begin. By the late Permian, life on Earth had been building complexity for nearly 290 million years without interruption. The ocean held reef systems that had been recovering and rebuilding since the Ordovician, now dominated by different coral groups than those of the Paleozoic's early chapters, but no less intricate in their architecture. On land, the therapsids, the advanced synapsids of the late Permian, had diversified into a layered ecosystem of herbivores, predators, and small opportunists that occupied nearly every position a terrestrial vertebrate could hold. The cynodonts, the most mammal-like of the therapsids, were thriving. The dicynodonts grazed in herds across the Permian floodplains. The gorgonopsids hunted them. The planet appeared stable. The ecosystems of the late Permian had been shaped by the extreme continental geometry of Pangaea, arid interiors, pronounced seasons, limited shallow marine habitat, and the organisms living in them were adapted to those conditions. They had survived the gradual oxygen decline that had ended the age of giant insects. They had survived the climate shifts that had fragmented the Carboniferous forests. The Permian biosphere was not a fragile one. It had been built and rebuilt across hundreds of millions of years of challenge. And the organisms it contained carried the accumulated biological solutions to every extinction event that had preceded it. In what is now Siberia, something was happening underground. Deep within the Earth's mantle, a plume of superheated rock was rising toward the surface, pushing against the crust from below. The land above it was not mountainous or geologically dramatic. It was a broad, flat region underlain by thick sequences of sedimentary rock, including enormous deposits of coal and organic-rich shale laid down during the Carboniferous, the pressure from below was building. Around 252 million years ago, the crust gave way. But the lava itself was not what killed it. What the eruptions released into the atmosphere was invisible, odorless at the distances that mattered, and operating on timescales that no organism alive could perceive as threat. Gases entered the air. The air changed. The oceans, which had been absorbing heat and chemical change for millions of years of Permian stability, began absorbing something different, and the consequences of what they were absorbing would not become fully visible until the systems connecting ocean chemistry, circulation, and biological survival had already begun to fail. But the ocean's response was not immediate, and it was not simple. It unfolded through a chain of connected deteriorations, each one creating the conditions for the next, in a sequence that meant the extinction did not strike all organisms simultaneously or through a single mechanism. Some species encountered warming first, others encountered acidification, others encountered oxygen depletion. The order in which those stresses arrived depended on where an organism lived, how deep, how close to the coast, how dependent on calcification or on dissolved oxygen. And none of those variations offered any group a reliable path to safety. But on land, the therapsids that had built the most biologically sophisticated terrestrial ecosystem the planet had produced were facing a version of the same problem, expressed differently. The Permian interior was already extreme. The seasonal swings, the aridity, the long distances between water sources, all of it had shaped the synapsids into organisms capable of tolerating conditions that would have been lethal to the amphibians they had replaced. But tolerance has a ceiling, and whatever was happening in the atmosphere was pushing temperatures, rainfall patterns, and the basic chemistry of the air toward ranges that the therapsids' considerable physiological flexibility had never been tested against. The Siberian traps were not a volcano. They were a flood basalt province, a region of eruptions so enormous and so prolonged that over approximately 1 million years, they released CO2, sulfur dioxide, methane, and halogen compounds in quantities that altered the global atmosphere. Crucially, the ascending magma intruded through thick coal and organic-rich Siberian sediments as it rose, releasing additional methane and triggering a feedback loop that amplified the warming beyond what the eruptions alone would have produced. CO2 drove warming. Warming reduced the ocean's ability to hold dissolved oxygen and strengthened stratification, trapping warm surface water above denser water below, with decreasing exchange between them. Stratification cut off oxygen delivery to depth. Anoxic zones expanded across the deep ocean. Sulfate-reducing microbes proliferated in those oxygen-depleted waters and produced hydrogen sulfide, pulses of which likely reached surface waters and may have escaped into the atmosphere. CO2 dissolving into seawater formed carbonic acid, dropping pH to levels that made it energetically impossible for calcifying organisms to build and maintain shells. Shallow tropical ocean temperatures may have risen 10 to 15 degrees Celsius within a geologically brief interval, and each stress amplified the next. The trilobites, survivors of the Ordovician extinction, the late Devonian extinction, and every other crisis across nearly 300 million years, were finally eliminated. Not because one catastrophe was powerful enough to kill them outright, but because the accumulated weight of interlocking stresses, each one degrading the resilience needed to absorb the next, exceeded what any amount of biological flexibility could withstand. The gorgonopsids were gone. Most dicynodonts were gone. The reef systems that had been a feature of Paleozoic oceans since the Ordovician did not return for 8 to 10 million years. The world, built since the Cambrian, was not erased in an instant. It was narrowed, pulse by pulse, until the corridor closed and almost nothing remained on the other side. But the question the great dying leaves open is not how the world ended. The extinctions are documented, the mechanisms reconstructed, the sequence of stresses mapped in rock outcrops on 5 continents. The question the great dying leaves open is harder than that. When 90% of marine species and 70% of terrestrial vertebrates are gone, when the food webs, the reef systems, the predator hierarchies that took 290 million years to assemble have been stripped away in what amounts, geologically, to a moment, what is left? Not what survived in the abstract, what actually crossed the boundary, what the world looked like on the other side, and whether anything that made it through or any resemblance to what 287 million years of compounding complexity had built. The extinction boundary at the end of the Permian is visible in rock outcrops around the world as a thin layer of sediment, sometimes just a few centimeters thick, that separates 2 completely different worlds. Below the boundary, the fossil record contains the familiar cast of the late Permian, diverse therapsids, abundant marine invertebrates, the reef-building organisms that had populated Paleozoic oceans for hundreds of millions of years. Above the boundary, most of that cast is absent. What the rock record shows in the immediate aftermath of the extinction is not a different set of equally complex organisms. It shows mere emptiness. The early Triassic, the period that immediately followed the Permian extinction, is one of the most ecologically sparse intervals in the entire fossil record. Paleontologists call some of the earliest Triassic rock sequences dead zones, intervals where fossils of large organisms are so rare that reconstructing what was living becomes a matter of piecing together fragmentary evidence from widely separated sites. The food webs that had supported the diversity of the late Permian did not transfer intact into the Triassic. They collapsed. What reassembled itself was simpler, dominated by a small number of generalist species that had survived not by being the most sophisticated organisms of their time, but by being the most tolerant of conditions that had become unlivable for almost everything else. But Lystrosaurus was not a success story in any meaningful ecological sense. Its prevalence in the early Triassic was not the prevalence of a superior organism. It was the prevalence of the only option available in a landscape that had lost the complexity needed to support anything more demanding. A single species filling emptied continents is not recovery. It is the biological equivalent of silence, structured just enough to look like sound. But the fossil record of the early Triassic shows something stranger than simple scarcity. Some of the earliest Triassic sequences contain what paleontologists call disaster fauna, assemblages dominated not by the survivors of the extinction, but by opportunistic organisms that expanded rapidly into the emptied ecological space. Microbes, simple invertebrates, organisms with fast reproduction rates and broad physiological tolerances that could colonize disturbed environments before more complex life could establish itself. The disaster fauna were not ancestors of the Mesozoic world. They were a temporary filling of a void, and their presence is evidence that what followed the extinction boundary was not recovery, but a period of genuine biological poverty that persisted for millions of years. But the cynodont lineages that would eventually produce the first true mammals were not thriving in that landscape. They were persisting, surviving in ecological margins, occupying niches too narrow or too demanding to attract competition from the few other surviving groups. The enormous biological inheritance of the Paleozoic, 287 million years of compounding complexity of arms races and extinctions and recoveries, had been reduced to a scattering of small, nocturnal, ecologically marginal animals whose survival strategy was based entirely on being overlooked in a world that had forgotten what complexity felt like. Lystrosaurus, a pig-sized dicynodont with 2 down-curved tusks and a horny beak, briefly constituted roughly 90% of all terrestrial vertebrate individuals on Earth after the extinction boundary. Not 90% of species, 90% of individual animals. A single hardy generalist filling emptied continents because almost everything else was gone. The Triassic landscape was not a recovering world in any meaningful ecological sense. It was a monoculture, and a monoculture is what life looks like when complexity has been stripped away and only the most tolerant generalist remains standing. The cynodont lineages that crossed the extinction boundary were small, nocturnal, and ecologically marginal. Exactly the characteristics that had allowed them to survive when the planet's background chemistry turned hostile. Within the first 10 million years of the Triassic, those cynodonts produced the first true mammals. Within the first 20 million years, a few archosaur reptile lineages produced the ancestors of the dinosaurs. The full recovery of ecological complexity took approximately 10 million years. A geological eye blink measured in years, but an eternity measured in generations of organisms trying to rebuild food webs from a devastated baseline. The Paleozoic fauna did not recover. Trilobites were gone permanently, ending a run of nearly 300 million years. The rugose and tabulate corals that had built Paleozoic reefs since the Ordovician were replaced in time by modern coral groups with entirely different biological origins. Large brachiopod communities that had dominated Paleozoic seafloors were reduced to a handful of surviving lineages and replaced functionally by bivalves and gastropods. The eurypterids were gone. The marine world that rebuilt itself in the Triassic and Jurassic was assembled from different groups entirely. A different ocean, reconstructed from the ruins of the old one. The 287 million year opening act of complex animal life ended not with a transition, but with subtraction. 90% of marine species gone, the remainder inheriting a planet that no longer resembled the one those species had built. If this reached you tonight, if the Paleozoic settled into something that felt worth the time, a like and a subscribe is the quietest way to say so. New documentaries arrive regularly here, each one built the same way. Slow, factual, and long enough to actually go somewhere. Rest well.